Welcome back to The Explainer. Today, we're heading far, far out to sea, miles from civilization, onto massive billion-dollar structures of steel and concrete. We're talking about offshore oil and gas platforms. Now, these structures pull highly pressurized, incredibly flammable hydrocarbons from deep within the Earth. It is, by its very nature, a dangerous environment. But today, we're actually not focusing on the danger. We're going to dive into the incredible automated safety net that quietly watches over everything. The Emergency Shutdown System, or ESD.
Think about this for a second. When a high-pressure line ruptures or a gas leak is detected, or worst case, a fire breaks out, how does a massive offshore platform react when seconds literally mean the difference between safety and total catastrophe? In these high-stakes environments, there is absolutely no time to sit and think. Human reaction time is just way too slow, and let's face it, human panic is way too unpredictable. If a worker has to run across a deck to manually turn a valve while a fire is breaking out, it's already too late. The platform has to be able to react completely on its own.
And that brings us right to the ESD. It is, for all intents and purposes, the automated nervous system of platform safety. Think about how your body instantly pulls your hand away from a hot stove before you even consciously register the pain. The ESD does exactly that. It instantly feels a problem through its massive array of sensors and reacts without a single millisecond of human hesitation. Its main jobs: selectively isolating the supply of oil and strategically venting high-pressure gas to get rid of the dangerous fuel. This automated reflex is exactly what stops a localized emergency from spiraling into a total disaster.
So, here's how we're going to break this all down today. We'll start with the nervous system concept, then trace the escalating hierarchy of defenses, levels 1, 2, and 3, and finally, we'll look at the hard-coded system logic and the rigorous testing that guarantees it actually works.
All right, part 1. The platform's nervous system and its hierarchy of defense. You know, the ESD isn't just one giant off switch that suddenly plunges the whole platform into darkness at the first sign of trouble. That would cause massive, unnecessary disruptions. Instead, it operates in a really strict escalating hierarchy. We start at ESD-1 for isolating specific equipment, move up to ESD-2 for a major process shutdown, all the way up to ESD-3 for total platform abandonment. And there's a vital rule to remember here. Each escalating level automatically triggers all the protective actions of the levels below it. It's a complete cascade.
Moving right along to Part 2, ESD Level 1, the unit shutdown.
Now, while the word shutdown sounds super alarming, ESD-1 actions actually happen pretty frequently during normal, everyday operations. It triggers any time a sensor detects an out-of-specification condition. Let's say a pressure transmitter detects excessively high pressure in a production separator. Instead of shutting down the entire facility, the ESD-1 simply closes specific block valves to isolate just that single unit. This allows the rest of the massive platform to just keep on operating safely.
The really crucial takeaway here is that Level 1 acts as a highly localized reflex. By boxing in just the problem area, ESD-1 buys the human operators in the control room time. It gives them the opportunity to investigate, figure out exactly why that separator had high pressure in the first place, and fix it. It stops a minor, totally manageable fault from causing a platform-wide headache, which minimizes lost production and keeps everything stable.
Okay, escalating things now. Part 3, ESD Level 2, Surface Process Shutdown. So, what happens when the problem is much, much worse? A confirmed fire, multiple gas detectors going off, or maybe an operator hitting a manual panic button? Well, an ESD-2 completely changes the game. It stops all oil processing immediately. It closes the block valves, and crucially, it slams shut the emergency shutdown valve on the export line and the riser boarding valves. This physically blocks any more hydrocarbons from entering the platform from the subsea pipelines. Historically, during tragic disasters like Piper Alpha, platforms were continually fed fuel from other connecting platforms. These boarding valves ensure the platform is completely isolated from that massive subsea fuel source. And at the exact same time, the system commands the vent valves to wide open. Opening those vent valves initiates one of the absolute most critical safety concepts in offshore engineering: blowdown. Blowdown is the deliberate, rapid venting of the entire high-pressure process inventory. All the oil and gas held in those vessels and pipes is routed directly to the flare stack. Think of the platform's process system like a giant pressure cooker sitting on a hot stove. If a fire breaks out around that pressure cooker, you have to empty the contents and relieve the pressure before the metal weakens and the whole thing violently explodes.
Let's look at the alternative for a second. If you do nothing during a fire, the vessel walls overheat, they lose their structural strength, and they rupture. This releases a massive, totally uncontrolled cloud of pressurized gas that instantly detonates in a catastrophic event known as a boiling liquid expanding vapor explosion. By initiating blowdown, you are deliberately sending all those dangerous hydrocarbons far away from the platform, straight up the flare stack, where they burn off safely in a massive, controlled flame. It is literally a life-saving maneuver.
And when it comes to blowdown in the offshore industry, there is a golden number you need to know: 15. This is the 15-minute blowdown rule, and it's governed by incredibly strict engineering standards. Once an ESD2 blowdown kicks off, the system must be engineered to drop the pressure inside those process vessels below roughly 6.9 bar gauge, which is about 100 psig, or to 50% of the equipment's original design pressure within exactly 15 minutes. It is a literal race against time and temperature.
Now for the absolute worst-case scenario. Part 4, ESD Level 3, Total Platform Shutdown. This right here is the ultimate point-of-no-return response. It's triggered when the situation is so severe that the platform is actively being abandoned. When an ESD-3 triggers, the platform effectively kills itself to save the environment and the escaping crew. It completely severs main power generation. The massive turbines spin down to nothing. The platform goes completely dark and quiet. Every single thing shuts down except for the absolute most critical survival systems running on battery-backed power. Things like emergency lighting to help the crew find the lifeboats and communications to coordinate the rescue.
The final and arguably most extreme action taken by ESD3 is slamming shut the SCSV. That stands for Surface Controlled Subsurface Safety Valve. It's an incredible fail-safe flapper valve located deep inside the well. Now, during normal production, hydraulic fluid pumped from the surface actually holds this flapper open against a massive heavy spring. When ESD3 hits, or say if the control lines are severed by an explosion, that hydraulic pressure is instantly vented away. Without that pressure, the spring takes over and forcefully slams the flapper shut, completely automatically. And the pure genius of the SCSV is where it actually sits. 60 to 90 meters below the mudline, sitting completely hidden inside the production tubing. This is the absolute final line of defense. Because it's buried so incredibly deep below the ocean floor, even if the entire surface platform is completely obliterated by an explosion, consumed by fire, or literally sheared off by a ship collision, the SCSV stays perfectly intact. It keeps that highly pressurized oil reservoir permanently sealed off from the ocean.
All right, let's look under the hood. Part 5, System Logic and Rigorous Testing.
So you might be wondering, how do we actually trust a computer to make these massive life-or-death decisions perfectly every single time? Well, the entire brain of the ESD is governed by a cause and effect matrix. It's essentially a massive, highly complex logic grid that maps every single possible sensory input, a high-pressure alarm, a gas detector, a fire detector, directly to a specific mechanical reaction, like closing a valve or tripping a pump. There's no artificial intelligence here guessing what to do. It is absolute hard-coded logic that is heavily scrutinized and approved by safety engineers and regulators during the design phase.
But hey, a perfect logic table doesn't mean a thing if the physical valve is stuck, right? So offshore safety engineering relies on incredibly rigorous testing. Every action is broken down into what's called a Safety Instrumented Function, or SIF, which undergoes formal Safety Integrity Level, or SIL, assessments. This mandates strict proof test intervals, usually every 12 to 24 months. Engineers don't just sit and check the computer code, they physically test the entire loop. They trigger the actual sensor, watch the logic process, and verify that the final physical valve closes within its required time limit.
It really is an incredible synergy of sensors, logic solvers, and massive mechanical fail-safes working perfectly together in one of the absolute harshest environments on Earth. Knowing how this automated nervous system works offshore, I'll leave you with this to chew on. What other invisible safety nets are silently protecting the complex infrastructure all around us? From the power grids keeping our lights on, to the chemical plants in our own cities. The engineering of safety is everywhere, just waiting to be understood. Thank you so much for joining me on this explainer, and I will see you next time.